Okay, so this is the single worst definition in the world, and us as markers keep asking them to stop giving it as a definition, but they don't ever stop. So you can't say isolated, which I have told you before. It needs to be closed. Closed in chemistry, isolated in physics, but that is a whole bunch of words. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will cancel the disturbance. So we really dislike them asking this definition, and they don't seem to be able to stop. So be warned, it's probably going to be in your exam. Then for 6.2, they are saying what is happening with the parallel lines after 5 minutes in graph A. That is equilibrium. So one of the definitions of equilibrium is the concentration of the reactants and the products remain constant. So that is what's happening for 6.2. You'll just see here on the memo, it's going to say that. So it's chemical equilibrium. So you didn't have to say chemical. So the concentrations of the reactants and products remain constant. The concentrations are constant. The rates are equal. So that's a very important thing that you're going to get confused about. The rates are equal. The concentrations are constant. The concentrations don't change, and the rates are exactly the same. Then, for 6.3, they're now asking if the forward reaction is exothermic or endothermic. And that's only for 1 mark, so I suppose you could just guess. But if you look carefully, PQ2 is a product. So PQ2 is a product. And in graph A, you end up with a concentration of 0.4 for PQ2. In graph B, in roughly the same amount of time. So it took 5 minutes in graph A, and it took 3 minutes in graph B. You get a concentration of 0.35. The difference between graph A and B is the temperature. So graph A is a lower temperature and graph B is a higher temperature. And at the higher temperature, you get a lower concentration of product, which would imply that the forward reaction was not favored when you increase the temperature. If you increase the temperature, you favor the endothermic, so that would mean that the forward reaction is exothermic. So let's just double check before I'm lying to you. See here, it's exothermic. So if I could just run through that again, when you answer these types of questions, so here they say explain for 2 marks, you increase the temperature and you favored the reverse reaction. You increase the temperature and you favored the reverse reaction because the concentration of PQ2 decreased. It went from 0.4 to 0.35, which means less of this was made, which means you favored the reverse reaction. And an increase in temperature favors the endothermic reaction. That's always true. So you tell me what happened in this case, and you tell me what else happened in this case. Then you tell me what always happens, and so then you now link them. If an increase in temperature favors the endothermic, and the reverse reaction was favored, that means that the reverse is endo, so that means that the forward is exo, because the one is always endo, and the one is always exo. I really love these questions. I've marked them so often as well. So it says there, with an increase in temperature, the endothermic reaction is favored, which I told you, and the reverse reaction was favored. Do not say this. Oh, why do they always put these bloody archaic reasons in here? Do not talk about that, please. Don't talk about that. So the concentration of the product decreases, which means the reverse reaction was favored. So they only asked for 2 marks, but I just like answering them, so I'll just say a lot. So sorry that you didn't want to. Then, for 6.5, how does the value of the equilibrium constant Kc for the reaction in graph B compared to graph A? B is smaller, it's less than, because the concentration of the products is less. And Kc is always concentration of products over concentration of reactants. So you can see there, it says less than. Then The next question is the big one. It's the 8-mark one, which Keegan actually got right in whatever exam, the June exam, I think. So I'm just going to go there quickly. Okay, so for 8 marks, we're going to look at this one. It says the equilibrium constant is 0.49 at 398. And 398 is this graph over here. They tell you that the volume of the container, I can't see it now. The volume of the container is 2. So it's a 2 decimeters cubed container. And so we don't really know what was happening initially, but we do know what was happening at equilibrium. So we know that the equilibrium concentration of PQ2 was 0.35, which means the equilibrium number of moles was 0.7. So if we start here, we can get that the equilibrium number of moles was 0.7, because that is just times by 2, you times it by the volume, which means the change, it went from 0 to 0.7, because they tell you that the reaction started with whatever that other stuff was, P something, and we do not include Q at all, because Q is a solid, so we did not include Q. So we only look at P2Q and PQ2. That's very confusing to say out loud, but anyway. So what we did now is we started with this number over here, and then we doubled it, and then we put it in the change column, which means that this is 0. The ratio between the reactant and the product is 1:2. So if this is 0.7, this is 0.35. We want to know what we started with for P2Q. That's what we want, the initial number of moles of P2Q. And that means that the change is x minus 0.35, and then we divide it by 2. I want to change this quickly and just make it a lot easier for you mathematically. If you ever end up with something like this at the end, just call that y, or I don't know, m or z or whatever, because then in here we can just sub in, we can just sub in a y, and then we can solve for y equals. So y equals in this case would be 0.35, I don't know how your maths is, squared over 0.49, and then that we can just work out as a number. So that actually ends up being a quarter. And if the y value is a quarter and the y value is equal to x minus 0.35 over 2, so that is a quarter, you can then solve for x. Minus 0.35 over 2. So you times it, why did I put a 4 there? You times it by 2 and you get 0.5. Then you add this part mathematically, you get 0.85. So you get what you get here. It's just easier to sub in y and then make y equal to the complicated thing. Mathematically, it's easier. But you do whatever you need to do to at least get some of those 8 marks, because that actually wasn't too difficult, I don't think. And another thing that you need to consider, I don't know why they do it like this, and I definitely don't agree, but this statement here, if you get this wrong, if you include the solid by mistake or do whatever other silly thing, if you get this statement wrong, you will get a maximum of 5 out of 8. If you leave this green statement out, you can get a maximum of 6 out of 8. So, yeah, you should probably just rather leave it out than get it wrong, if you can help it. Then, for 6.7, they say describe the change made at the equilibrium system in the 8th minute. So describe the change, and they tell you that it is constant temperature. They tell you it is constant temperature, so something happened, and you can't tell me that they added reactant or product. You can't tell me that they added reactant or product, because what happened is this one went down and then up, and the other one went down. Both of them changed immediately. Both of their amounts, their concentrations, immediately dropped. And the PQ2, this one, enjoyed it. It favored the forward reaction afterwards. It made more PQ2, but the P2Q, the reactant, went down. So this picture, if you can understand, what's happening here is you are favoring the forward. And you did nothing with the temperature. It tells you it's a constant temperature. So what we twiddled was the pressure. If I favored the forward reaction, what I did was decrease the pressure. And if you decrease the pressure, you increase the volume. Concentration is number of moles over volume. If you increase the volume, you're going to decrease both the concentrations. Immediately both of these went down because you increased the volume to decrease the pressure. And because you increase the volume, it's at the bottom of the fraction, which means they're inversely proportional. So if the C goes down, the V goes up. If you increase the V, you decrease the C. But afterwards, you are favoring the forward reaction because decreasing the pressure will always favor the reaction that makes more moles of gas. So that's what happened there. Ooh, sherbet, option 4, I don't want that. Okay, let's just take that away. So basically, you have decreased the pressure, or the volume of the container was increased. I said both of those. And then explained by using Le Chatelier's principle, the amount of P2Q increased because decreasing the pressure will always favor the reaction that increases the moles of gas. If you decrease the pressure, you're making more space, and so the reaction wants to take up more space by making more products. So you gave it more space, you decreased the pressure, you made the container bigger, and so therefore it made more product to fill up that space.